Hello, this is a sound test. Ah, it works. We'll be here soon. Hello, everybody, and happy Monday. Good to see you all, and welcome to our daily show. This is Ask Math Anything, and I'm Po-Shen Loh, your host. What we do in this kind of a show is we answer questions that come from anywhere in mathematics. So this is not necessarily the same as the usual math class that you attend, and then that's in part because you already have a math class to attend, and I'm not looking to replace that. Instead, what I like to do is I like to see what kind of questions people are interested in, and then we'll give some lessons around them. Generally speaking, I'll try to choose questions where I can talk about the answers in terms of algebra or geometry, because I know that that's what many of the people who are attending this are thinking about. But of course, what you'll soon see is that these questions can range quite widely across all different areas of mathematics and science and other things as well. If you're new here, welcome. And if you've been here for a while, as I can tell with people commenting on the shirts, welcome back. Let's see, what kind of questions should we talk about today? Aha. So I'm seeing a bunch of different questions come here. What we always do is we try to see if there are any questions that I can maybe tell some interesting mathematical story about. Great. Okay, so I see another question. Somebody said, ratios are still useless and still don't make sense. So let me tell you something I was doing today that I finally realized that the ratio was the way to go. So there was something I was doing where I was actually writing a computer program, and I was trying to find out if there was a signal that had come in. And this is using something fancy. It's called the Fourier transform, but that's actually not an important part. What is important is that I was using a computer to do it, and the computer said the signal is sort of like how much intensity is there over some amount of time. And in particular, what happened is that the amount of time that you could ask it to listen for had to be some amount of time that was a power of 2. So this is a power of 2. Okay, well, how do you measure the time? It's in some certain units of time. The units of time were technically like fractions of seconds, but the number had to be a power of 2. And I was trying to figure out, what should I do? I have a particular signal that I'm listening for, and the signal's length is not a power of 2. But the way that this thing worked is you could go and try to find out how much of your signal was there and how much background noise was there, and it actually ended up not mattering. Because if you just went and said, grab a power of 2, which is bigger than your signal, when you look at ratios, the ratio was the same. Let me try to find a way to explain that in a more simple way. The more simple way might be saying, let's suppose that you have some length of road, and on this road, let me try to draw a road. So we have a road. And the road's pretty long. But along this road, there's a stripe that's down the middle, maybe a yellow stripe. And this is supposed to be like a solid stripe. Okay? Now, suppose what you're trying to do is you're trying to find out how wide of that stripe, like how intense that stripe is. When I say intense, what I mean is that, there's a yellow stripe that's going across here, but it's almost like how thick is that yellow stripe? Now, there are different ways that you could try to do this. Actually, wait, I should be clear. Maybe I should actually adjust what I said. Actually, now I'm trying to think if I can turn this into the right kind of analogy. The right kind of analogy I'm thinking of is one where, let me see. So you see, now I'm starting to think. The reason, and you're watching me think, right? So the way I'm thinking through this is, how can I find a way that's easy to explain this to lots of people? If there happens to be some signal that I'm trying to detect here, and there's also some kind of a background noise, which is that there's this background here which has a lot of zeros, then, okay, so the difficulty thing here is that, as you can see, I'm trying to think how to explain something that comes from something that's more advanced in order to be as understandable as possible to people who are trying to learn ratios. And unfortunately here, it looks like it might be a little bit difficult to translate that advanced thing down. Instead, I'm going to say it in a different way. Okay, so let's not use the road. I have a different idea. Here's the other idea. Suppose that you have, actually, let's just do it this way. I'm going to write down two fractions, okay? I'm going to write down two fractions. And one fraction is, now I'm trying to think. Yes. So let's do it this way. So I'm going to write down two fractions, okay? So one fraction is 1 plus 1 plus 1 plus 1, and then plus 0 plus 0, divided by 2 plus 2 plus 2 plus 2 plus 0 plus 0. Okay, so what did I do here? What I did here is I have something which, this is supposed to be the signal I'm talking about that I'm sensing. On my denominator, I have a bunch of 2's being added together. On the numerator, I have a bunch of 1's. The question is, what are ratios good for? And the answer I want to give is that, you see, when you're doing something with ratios, somehow the ratio between the top and the bottom is still 1/2, even though there's a lot of 1's and a lot of 2's, and even when there's a lot of 0's which are added at the end. So this is something that ratios are useful for. It's almost like actually, here's how I should explain it. This is what the context is that I was dealing with. There's basically something where there's a sound that's being emitted. And I'm sort of looking at the volume of the sound that I'm hearing as a fraction of the maximum possible volume. And the maximum possible volume is 2. And what I'm hearing is a lot of 1's. So it looks like it's half. But the way that I had to do this in the program, you actually also sometimes had to just listen for longer. And when you listen for longer, you're listening during a time when your thing that's supposed to be blasting isn't blasting anything at all, and it's sending out zeros. So here's something kind of interesting. When you write a fraction like this is 1/2, but this is also 1/2, even if I add more zeros on top, and even if I add more zeros on the bottom. So I think what I'm referring to is that if you wanted to know whether or not some signal had arrived, looking at the ratio of what you were measuring on top divided by the ratio of what was being emitted on the bottom, as long as it was still 1/2, you know that you were emitting like 1/2 of the volume that you could emit. I guess that's what ratios are generally good for. Ratios are generally good for saying, what is your potential? Actually, that's what this is probably good at explaining. Like, what's your potential? If the potential is that you could emit this amount of stuff, this amount of noise at certain times, but at certain other times, you just can't emit because somehow the speaker is off. But, you're looking at it as a percentage of a whole. Then if you want to know, have you gotten a signal? You just look at what did I receive divided by what was I able to emit. And that's sort of like points that you got out of points that you could have earned. And that's where ratios are useful. And if I want to put this in contrast, if you just simply try to say, do I hear a total of at least some amount? Well, what's your total out of? And maybe let's put it into grades, right? I guess this is what we also think about in school. You don't really say a person gets an A if they got at least 623 points. Out of what, right? The question is out of what? It's only relevant if you know it's 623 points out of something like 625 points. So I hope this gives some answer for like what the ratios are good for. It's like what I was trying to do is I was trying to detect whether or not a signal had arrived by listening on a microphone. And I was trying to think of it based on out of what is the maximum the microphone is able to record. And that's sort of like saying if I take a class, I want to know whether I got some kind of a score or some kind of a grade. I cannot just go based on the number of points I got. I have to know what it's out of. Okay, well now we've gotten started, we talked about some math. At this point we probably also have some other questions that we can maybe talk about. Oh, I see a question already. Jiang Michael asks, is 1/2/2? What is this? The question is, what is this? And here's how I'll explain it. It depends on how you decide to interpret it. And if you interpret it the way that a computer will interpret it, here's what you do. You use, these are division signs, and division signs are evaluated from left to right. So in fact, the way that this is evaluated in a computer is it does 1, and then it divides by 2, that's half, and then it divides by 2 again, and that's 1/4. So a computer would actually say that this is 1/4. If you want to understand why the computer would think that way, here's another way you can think of it. What would a computer think of 1 minus 2 minus 2? Do you know how this is interpreted? I see that we had some lag. Sorry, the internet sometimes has issues, but I'm glad that we're all back. So we have, if I wrote 1 minus 2 minus 2, what would that be? Oh. What would we get here? If we did 1 minus 2 and then minus 2, everyone answers, of course, it's 1 minus 2 is -1, minus another 2 is -3. And that's because you're evaluating from left to right. And so if I go over here, that's what I should do here as well. I should do 1 divided by 2, and then divide by 2 to get 1/4. The question that was asked is, but is the answer 1? If you want the answer to be 1, you would need to do this. 1 divided by parentheses, 2 divided by 2. And now that would be 1 divided by 1, which is 1. So that's how you would get the 1. You need to put parentheses in. The question of what we're doing. Nice QQ. What we're doing is we're talking about how you interpret expressions that look like this, 1/2/2. Although since I did say something about computers, depending on what programming language you're using, if you write down 1/2/2, you might find out that in certain programming languages, such as Java, which is what I was using earlier today, some computer might say 1/2/2 equals 0. Does anyone know why the computer might say that? C++ would also say 0. Does anyone know why a computer might say the answer is 0? It's not 0. I mean, how could it be 0? You have stuff dividing by stuff. Like 1 divided by stuff. How could it ever be 0? It's dumb. Oh, no, Ian Ray is right. It's doing what's called integer division. So if you have a computer program, I don't remember exactly. I think Python might do things with decimals. I'm not really sure. But I do know that C++ and Java and some of these fast languages, the way that this works is it does integer division. When it has an integer, a whole number, 1, divided by another integer, 2, as it's doing this part, it does 1 divided by 2 as an integer. And when it does integer division, it throws away the remainder. So actually, in these computers, if you do 1 divided by 2, the answer is already 0. Because 1 divided by 2 is 0 with a remainder of 1. So yes, it rounds it down. So the answer to this is actually 0. Because if you divide that by 2, you also get a 0. If you're ever programming a computer, if you want to get something that's not 0, here's a random tip. I don't know if you guys are into programming computers, but if you write 1.0/2/2 and you put this into C++ or Java, what you will get is 0.25. And the reason for that is because once you put a 1.0, you just told the computer, just kidding, it's not an integer, it's a decimal. And since it's a decimal, please do the whole thing as decimals. Scratch says 0.25, right. So there are a lot of other types of computer programming languages. Some of these will automatically turn them into decimals. Actually, if you're curious, some of you might be wondering, why doesn't everyone just use decimals? There's a really good reason for that. How would a computer store a decimal anyway? You see, inside your computer, it's very inconvenient to store a decimal because a decimal might have infinitely many digits. So it's hard for a computer to know exactly how big something is. For example, try writing down 1/3. What is 1/3? How might you try to write 1/3 as a decimal? You see, if we try as humans, we do this. And we have to keep going. But somehow you can't really stop. It's not fair to stop. And you can't really tell the computer, it just goes repeating, right? So in fact, it's not convenient to ever do anything with what we call floating point numbers or decimals. It's very inconvenient to store decimals in computers. If you wanted to store this, you'd almost want to store it's a 1 divided by 3. And if you ever used Wolfram Alpha, in Wolfram Alpha, if you write 1/3 or 1 divided by 3, it'll do it exactly and it'll give you fractions. But in Wolfram Alpha, if you type 0.3333, just hold down the 3 and get tons of 3's, your answer will always be rounded off afterwards. So indeed, it's actually quite hard to store decimals. And that's why a lot of these programming languages, as long as you can stay in the whole numbers, it's much better. You don't have to worry about whether it's exactly equal to 0.3333 or if it's like 0.333337 or something like that. Actually, let's now do something else. This just inspired me to talk about another problem. How do I write 1/3 in base 2? Because you see, a computer is not going to store this. This is our base 10, right? Remember, I've talked before about what base 2 means. Base 2, if I want to write 1/3 in base 2, what you have to do is you have to actually think about place value now. How might we do this? And is there some clever way to do this? So let's see. In base 2, it's going to be, is there going to be anything in front? Well, no, it will be 0 point something. But then point what? 0 point something, 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 something. It's going to go on forever, right? So now what do we do? Well, we have to know how much each place is worth. This place is worth 1/2. This place is worth 1/4. This place is worth 1/8. This place is worth 1/16. This is worth 1/32. And this is worth 1/64. Who can help me with this? I'm looking for some help. I want to convert 1/3 into base 2. I see that people are saying there's a lot of lag today. The lag is quite possibly because I tried turning on ultra low latency so that you guys can see like right away after I say something, and then you would be able to answer faster. But how would we do this? Anyone got ideas? Let's start with the beginning. 0 point what? What should the first digit after the decimal point be? Should I go with 0.0 or should I go with 0.1? What do you think? In binary, you have to say 0.0 or 0.1. I see that Caleb T, Caden C says 0. I got a bunch of zeros coming here. So it looks like some people are saying zeros. Let me say why 0 is the right answer. The reason 0 is the right answer is because if you put a 1, you'd already get a half. A half is big. A half is bigger than 1/3. And that's not what you want. You don't want that big. If it's bigger than 1/3 already, then it's too much. So I should put a 0. Now, the next thing is 1/4. Should I take a quarter? Think of this as almost like making change, right? I have a third that I need to make. And, oh, a quarter arrived. A quarter is less than a third, so let's go ahead and take the quarter. If I take the quarter with a 1, what that means is how much is left. If I think about what's going on here, how much is left? How much is left is 1/3 minus 1/4, which is 1/12. If I have 1/12 left, should I take this 1/8? No, 1/8 is unfortunately too big. I have to make 1/12, and 1/8 is too big of a chunk. So let's not take it. Okay, the next thing is 1/16. Now I can take 1/16 because I have 1/12 I need to add up to, and so 1/16 is less than that. So let's take that. Okay, the next thing I need to do is I need to say, if I've taken the 1/16, now I need to subtract again. So how much is left from here on out? This part, the amount left, my little arrow means like from here to the rest, what does it add up to? And what it has to add up to is it has to have left over 1/12 minus 1/16. And what that is I have to subtract fractions. What is this? Can anyone help me with 1/12 minus 1/16? Well, 12 is 4 times 3, and 16 is 4 times 4. So it looks like my common denominator will be 4 times 4 times 3. 4 times 4 times 3. And my numerator is the 12 is going to give me a 4, minus the 16 is going to give me a 3. So it's 1 over 16 times 3 is 48. And I see some people have an answer. It's not this one, and it is this one. Gee, it looks like it's a repeating decimal. It's 0.01010101. Okay, that's nice. Do you believe this? How would I know whether this is right or not? I could try to add up all these fractions, and that will be 1/3. If I add up 1/4 plus 1/16 plus 1 over 64th and so on, watch, it actually does work. That's what this binary means. If I say 0.010101, then that means that I want to add a quarter and a 16th and a 64th and all these powers of 4. Let's check. 1/4. Oh, let's suppose I don't know what it is. I'll call it S for sum. 1/4 plus 1 over 16 plus 1 over 64 plus 1 over 64 times 4. 256, maybe? Oh, how do you add this up? Does anyone know a good way to add this up? David Shan, what is the question? The question is, what is this? 1/4 plus 1 over 16 plus 1 over 64 plus 1 over 256. What is this? And if you want to know what we're trying to do, we were trying to write 1/3 in base 2, in binary. And how would I know what this is? This is a sum. Oh, we kind of know the answer better be 1/3. But how would you know? Oh, it's the infinite geometric series formula. Well, you don't need a formula for this. If this is S, where I don't know what S is, here's one way to think about what this is. This is S. And over here, what's this bit? This bit, if I go on forever, is actually exactly 1/4 of S. It's because 1/4 of S would be a quarter of a quarter. Oh, that's a 16th. Plus a quarter of a 16th. Oh, that's 1 over 64. Plus a quarter of 1 over 64, which is 1 over 256, and so on. Right? So from here on out, that just happens to be 1/4 of S. And that actually works because S converges, but we won't get into that today. Continuing on, now I know that the sum is equal to 1/4 plus 1/4 of the sum. And if I just subtract a quarter of the sum from both sides, 3/4 of the sum is equal to 1/4, and so the sum is equal to 1/3. So this is one way of seeing that the answer is 1/3. And so at this point, if I go back here, indeed, this point 010101, that's 1/3 if it goes on forever, repeating. Okay, now I want to tell you why I decided to talk about this. Why I wanted to convert 1/3 into base 2 is because there's another way to convert 1/3 into base 2 where you can get it right away. And the way is to first convert into base 4. For this, I want to maybe talk about some base conversions because this is fun. Hey, I have a question. The question is, here's some number in base 4. 2, 3, 1, 0, 3, 2, 1 in base 4. Can anyone help me convert this into base 2? Oh no, this looks like it will be horrible. This looks like it will be no fun at all because how do you do this? Well, you first convert from base 4 to base 10, and that's by thinking of place values, like this is a 1, this is a 4, this is an 16, this is a 256. Do you do that? Do you first convert this into normal base 10 and then convert that back into base 2? That would be bad. That would take a huge amount of time. But instead what you do is you think about what this means. Let's go in a circle. So first I'm going to say, what does this mean? Let's write it down as stuff times multiples of 4. Powers of 4. What this is, well, let's go with this first. There's a 2 in front. It's 2 times 4 to the how much? Now I have to count. This is hard. All right, 4 to the 0, 4 to the 1, 4 to the 2, 4 to the 3, 4 to the 4, 4 to the 5, 4 to the 6. Why in the world did I write so many of them? Oh well, I'll just do it. 2 times 4 to the 6 plus 3 times 4 to the 5 plus 1 times 4 to the 4 plus 0 times 4 cubed plus 3 times 4 squared plus 2 times 4 to the 1 plus 1 times 4 to the 0. Okay, now I want to turn this into base 2. Watch. I'm going to turn it into base 2 where I do something to each of these rows. That's why I wrote these all as rows. Big equal sign. Let's start from the bottom. 1 times 4 to the 0. Well, 4 to the 0 is just 2 to the 0. And in fact, I can write that 1 times 4, sorry, it's not, it is just 2 to the 0, but the more interesting thing is it's 2 to the power 2 times 0 as well. We'll see. So if I go all the way down, the very bottom row, I could write this as 1 times 2 to the power 0 plus 0 times, actually let me think of this, I have a better way of doing this, okay? I'm not going to write it this way. I'm going to do some parentheses. I'm going to say that the bottom thing happens to be 0 times 2 plus 1 times 2 to the power 2 times 0. I'm writing it this way so I can find a big pattern, okay? So 1 times 4 to the 0 is just 1 times 4 to the 0, right? 1 is 0 times 2 plus 1. This is 4 to the 0 because 2 to the 2 is 4. Let's do this with the next one. For the 2 times 4 to the power 1, that's equal to 1 times 2 plus 0 times 2 to the power 2 times 1. And that's because 4 to the 1 is 2 to the power 2 to the 1. Okay, let's keep going. When I go to the 3, I'm going to write the 3 in binary. 1 times 2 plus 1, that's 3 in binary, times 2 to the power 2 times 2. I'll write 0 in binary also. 0 times 2 plus 0 times 2 to the power 2 times 3. 1 becomes 0 times 2 plus 1, 2 to the power 2 times 4. The 3 becomes 1 times 2 plus 1, 2 to the power 2 times 5. And finally on top, we have 1 times 2 plus 0 times 2 to the power 2 times 6. Okay, what was the point of doing this? The point of doing this is something in binary. Look, all of these are either 1 or 0 times the power of 2. Let's do one more equals. I can actually write it from the top now. You see, this is 1 times 2 to the power 2 times 6 plus 1. So that's 1 times 2 to the power 2 times 6 is 12 plus 1 is 13. I have a 0. It's plus 0 times 2 to the power 12. Now the next line, I have a 1 times 2 to the power 11 plus 1 times 2 to the power 10. So this is very powerful. You see this? This 1 times 2 times 2 to the 2 times 5. 2 times 5 is 10. But when I multiply 2 to the 10 by another 2, I get 2 to the 11. And this 1 is still here. But this 1 is with the 2 to the power 2 times 5, which is 2 to the 10. That's there. Now we keep going. The next thing that happens is this 0 times 2. That will go to 0 times 2 to the power 9. The 9 is because I had a 2, and I had a 2 to the power 8. And that's 2 times 2 to the power 8 is 2 to the power 9. And the next one is 1 times 2 to the power 8. Do you see this beautiful pattern? My powers are 13, 12, 11, 10, 9, 8. I'm getting a binary representation. The next thing that comes is 0 times 2 to the 7 plus 0 times 2 to the 6. And then I get 1 times 2 to the 5 plus 1 times 2 to the 4. And then I have 1 times 2 to the 3 plus 0 times 2 squared. And then I have 0 times 2 to the 1 plus 1 times 2 to the 0. So what you see is a very powerful thing that you get to do. If you ever have to convert from base 4 to base 2, you take each of the digits in the base 4, you convert each of them into the base 2 version, and then that happens to be your perfect base 2 representation. I can now write the whole answer. It is 1, 0. That's from converting the 2. That's the 1, 0. And then I convert the 3, 1, 1. Then I convert the 1, 0, 1. Then I convert the 0, 0, 0. Then I convert the 3, 1, 1. Then I convert the 2, 1, 0. And I convert the 1, 0, 1. Boom! I hope I got it right. Let's double check. 2, 3, 1, 0, 3, 2, 1. Yes, that's it. So actually, this is amazing. This is very powerful. If you ever want to convert from base 4 to base 2, you just take each of the numbers, you convert each number into base 2, and then you go boom, 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 put them all down, and you are done. Cool. Yes, I also thought this was really cool the first time I saw it. And now, let me tell you why I told you I saw something interesting about 1/3. Because I didn't do the 1/3 by converting it into base 2 when I was checking it. I converted 1/3 into base 4. 1/3 in base 4 is 0.111, 11111, repeating. It's the same reason, for the same reasons that 1/9 in base 10 is 0.11111 repeating. Actually, you can also see this because if I took this 0.11111 repeating, multiply by 3, I get 0.333333 repeating, which in base 4 is 1. The same reason that 0.99999 repeating in base 10 is 1. And so I just have to convert this into base 2. So, in base 2 is, just take each of the base 4 digits and write it in base 2. 0.01010101 ... And you're done. Okay, so this is the question. How did we get to this question? I'm not really sure. I think it came from because somebody asked us 1 divided by 2 divided by 2 equal to 1 or 1/4. And then we ended up talking about all of these different things. But all of these different things, as you can see, are connected. Okay, let's go. And thanks. Yes, I actually do think this is a nice way to kind of tie together a lot of different ideas all into one. Let's see, what else can we do? More questions. Okay. So Minko has asked, Prof. Po, do you get discouraged when you make a mistake in a math problem? Well, I make mistakes all the time. You've seen me give live streams. I make mistakes all the time. I don't know I'd say I get discouraged, but what I would say is that if I make a mistake, the thing that goes into me is, gee, I hope I can not make the mistake next time. And you always see if you can learn from your mistakes. So I encourage you to do that. I also saw another question. This is quite interesting. Somebody asked, Leo Yu asked, how do negative bases work? So usually people don't use negative bases. The idea of a base is that it's a way of representing numbers where you say, I'm tired of writing different symbols. I have symbols from 0 up to 9. That's enough symbols. I don't want more symbols. And then you just use the next place to represent. For you guys, it's next place this way. Next place to represent the place value. When you have negative numbers as the basis, it's just not very convenient because what does it mean to go from 0 up to that negative number? So I think the real way to answer this question is, what is the purpose of the basis anyway? The real purpose of the basis is just to provide a way for us to represent numbers. And the most useful kinds of bases then are whole number bases, which are positive. Okay, what else can we have here? Okay. Somebody has asked, I'm good at math, but I don't like it a lot. What should I do? That's normal, actually. A lot of times when you start doing something, you can become good at it without really realizing that it's fun. I think what I'm hoping to do is through these kinds of live streams and this kind of discussion, you can see how it's just kind of neat to see how everything connects together. And the way that you can find math more interesting is if you yourself spend your time trying to connect things together. I always find the connecting and these nifty ways to do questions to be way more interesting than just getting the answer. And so my hope is, if you attack math that way, and sometimes you're like, wow, that was a cool trick. It's almost like how when people play sports or play other kinds of games, you sometimes get this feeling of like, that was just a really slick move. And sometimes the response is, it's a beautiful kick or it's a beautiful toss. There can also be beautiful approaches to do math. And that can be one way to enjoy it. It's not just something that you have to do in order to get a result. And actually, there's a certain pride. I should add that there's a lot of pride that can come when you feel like you're capable of doing something. And so my hope is, if you're good at math, it'll help to make you feel more confident or more powerful at being able to do something. Because in the end, you should be able to evaluate yourself and you should be able to feel good yourself based on what you can do, not just based on what other people say about you. You're the most strong if you can know that, yes, I'm actually worthwhile, I can do some stuff. And through math, you can actually get that too. More questions. Somebody's asking me, have I learned the rules of chopsticks yet? Unfortunately not. Our team did send me the rules, but I just didn't have the time to go and dig in. And I'll explain why. It's because for me, when I see rules of a game, the way my brain works is once I see rules, the immediate thing I think is, gee, what can I do within these rules? Because rules are some walls, but it's always fun if you can find some creative way to play within those walls. So I was actually a little bit afraid that if I start reading those rules, I'll start spending a while thinking about, what can we do? And I didn't quite have that time at the moment. We'll get there someday. Batmobile. How can I train my mental math? Asks Batmobile. When you're doing mental math, I think that one of the important pieces is focus. It's important to be able to be like, yes, there are birds outside, or there's a thunderstorm, or it's bright, or whatever. No. There's only me and what I'm trying to do. So this is a certain focus. Similarly to if you were doing sports, when you're shooting a free throw, you presumably don't want to be getting distracted by all kinds of other people around you. So mental math, you want to be able to focus your brain on something. The next pieces that can help in the mental math, here's a random tip. If you actually it's fun to learn these neat tricks that can help you multiply or add things more efficiently without making mistakes. Like there's a fun trick, if I want to square a number ending in 5, like 35, I just take 3 times the next number, that's 3 times 4, that's 12, and the answer is 1225. So I'm just saying these are fun tricks. And if you kind of go around and I guess try to collect these tricks and also try to understand why they work, your mental math will also be stronger. But to me, mental math is just something which is it's an art form. I don't personally think it's that extraordinarily important. I don't think a person is smart or dumb based on whether they can do mental math or not. On the other hand, it's a fun way for me to look at problems and say, I wonder if I can find a creative way to do this all in my head. And if you approach mental math that way, you might be better. Other questions? Oh, okay. Here's a question. Oh. There's a question. There are different kinds of questions. I'll take something here, which is this is a math question first. Andrew Chow asked, "Why is the square root of a number usually irrational?" Well, here's a way I can answer that. So when you're taking the square root of a number, right, and you're asking why is it usually irrational, a lot of times when you're taking the square root, you're taking the square root of whole numbers. Let's start with that, okay? So if you're going to take the square root of a whole number, like square root of 10, is that going to be rational or irrational? Here's how to think of it. Square root of 10 is something which when you multiply it by itself makes 10. Can you multiply two fractions, like legitimate fractions with numerators and denominators that don't cancel? Can you multiply two fractions that don't cancel by each other and get a whole number? Actually, no. Whenever you multiply two things that are already fractions in their reduced form, let me make an example. Let's pretend I reduced the form already. Suppose I had something like 6 over 35. That's a reduced fraction. You cannot cancel anything. And if I multiply it by itself, 6 over 35, because I couldn't cancel before, there's nothing to cancel now either. And so this is going to be an even worse fraction. Oh, 35! That's a number I just said. 35 squared is 3 times 4 is 12, 25. Mental math can be fun. Okay. 36 over 1225. And you cannot simplify that. The reason you cannot simplify is because you couldn't simplify before. And if I just have another copy, it's useless. The 35 is not going to help me cancel anything from that 6 either. Okay? So, if I wanted to look at the square root of 10, there's only two options, really. It's either going to be a whole number or it's going to be irrational, not writable as a fraction. Right? When I look at this, if I multiply together two legit fractions that have tops and bottoms, they multiply and you still get a legit fraction. So the square root of 10, oof, says somebody. I'm not sure if Lily Ma's oof is in response to this multiplying fractions and not getting a whole number or something else, but I'll take it as a response to this one. The square root of 10 is either going to be an integer or irrational. Okay, but if I know it's either an integer or irrational, now you can also see why it's more rare for it to be an integer. Because it will only be an integer if you happened to have chosen a perfect square. And perfect squares get farther and farther apart because you're multiplying two numbers by each other, right? So at this point, how could you get an integer? In order to get an integer, you would need a perfect square. Like square root of 1, square root of 4, square root of 9, square root of 16, square root of 25, square root of 36, square root of 49. And if you see what's happening, these are getting, like the numbers inside the square roots, they're getting bigger. Yes, Irfan, thank you. Perfect square is rare. It's because the numbers, like the number of perfect squares less than 100 is only like around less than or equal to 100. Number of positive perfect squares less than or equal to 100 is only 10. And the number of positive perfect squares less than or equal to 10,000 is only 100. And so they get more and more sparse as you keep going. They get more and more sporadic. There are fewer and fewer of them. And so the idea is the perfect squares themselves are rare. And so that's actually why if I take the square root of a whole number, it's usually irrational, because I would be lucky if I happen to pick a perfect square. Similarly, if you happen to go and take the square root of a fraction, you'd only be able to get a whole number, you'd only get a rational number, you would only get a rational number if somehow after you cancelled the fraction, both your numerator and your denominator were perfect squares. I saw somebody say a very interesting comment though. The number of perfect squares is actually the same as the number of integers. That's true. I mean, this is 1, 2, 3, 4, 5. I could count all of these, and I would count, and it would take me the same amount of time, in the sense that I could say, hey, this particular number from 1 to infinity, you don't get to infinity, but this particular positive integer corresponds to that particular perfect square. So they are in what we call one-to-one correspondence. However, although it's true they're the same number of them, what the question was asking was not like, are there the same number of perfect squares as the number of integers? It asks, when I'm doing problems, why does it seem so rare? And the reason it seems so rare is because when you're doing problems, you usually don't do problems with like numbers from 1 to, your numbers are usually like 1 to 1,000 or something. And between 1 and 1,000, I mean, how many perfect squares are there? Like 31? Oh, let me tell you how I did that in my head. So what I said is the number of perfect squares is 31. It's because I remembered that there's something in the 30s, and I was trying to square some numbers. And I want to show you something cool. 30 squared is easy, 900. And that's how I knew like 1,000 is going to be around 30 squared. What's 31 squared? 31 squared. Well, I could try to multiply that. 31 times 31. 1 times 1 is 1, 1 times 3 is 3, 3 times 1 is 3, 3 times 3 is 9. 961. Okay. There's a way to do that in your head. The way to do the 961 in your head is to say 31 squared is actually 30 plus 1. Whoa. 30 plus 1 times 30 plus 1. And if you expand this out, then it's going to be, if you've been following our live streams for many days, you probably are used to this kind of thing by now. If you just try to multiply the brackets, the 30 times the 30 is 30 squared plus, and then what happens is I get a 30 times 1 plus a 1 times 30. That's 2 of them. 2 times 30. And then finally, I get just the 1. 1 times 1. strictly speaking, I should actually write it out a different way. I should say 2 times 30 times 1 plus 1 squared. And this is a pattern. The pattern is somehow a plus b whole thing squared is equal to a squared plus 2ab plus b squared. You may have seen that before. And so if you know this, then as you're doing this in your head, you say, okay, 30 squared is my 9, my 2 times the 30, that's going to give me a 60, and then put a 1, so 961. Done. But there's something else that's also kind of nifty. Does anyone know what is 13 squared? 3 times 3 is 9, 3 times 1 is 3. Okay, 3, 1, 9, 6, 1. Oh, 13 squared is 169. And maybe you know that because you've done that problem so many times. Hey, why are these two flipped? Why is 13 squared the flip of 31 squared? That's interesting. It's because you're doing the same thing. I mean, first of all, you can see that the numbers that are going here, that 9 goes there, the 3's are still in the middle, and the 1's over there. Wow, yes, this is cool. And actually, if you look at what happens next, if I wanted to do the 13 squared, that's just 10 plus 3 times 10 plus 3. And so the same logic tells me it's 10 squared plus 2 times 10 times 3 plus 3 squared. And the important thing is that's the 100, that's the 60, and that's the 9. It's the same kinds of things that we were multiplying together. Cool. By the way, it works for other stuff too. Does anyone know what is 21 squared? Okay, 2 times 1, 1 times 1 is 1, and there's a 2. I think this is right, 2, 4. That middle 4 looks like a 9. I'll rewrite it. What do you think? 441. Why is that what you might expect now because of what we just saw? Does anyone know what I'm getting at? What's so nice about 441? Aha. Oh, yes, Tiger Lee, you're really funny. Tiger Lee wants me to compare 11 squared and 11 squared. Good. But yes, this is like, yeah, it works for 11. It works for 12. Wow. Hey, does it work for 30? It actually works for 30. What happens if you flip 30 around? What's 30 flipped around? It does, actually. 30 flipped around is 0, 3. And if you square 0, 3, it's 0, 0, 9. It works also. But then somebody says, okay. The party has to end. The party is that it doesn't work when you go to 41 squared. But why not? Does anyone know why it breaks when you go to 41 squared? What's going on with the 41 squared? You see, there's a 14 squared and there's a 41 squared, right? If I do 14 squared, 14 times 14, all right, 4 times 4, 16, 4 times 1 is 4, this is hard, 56, okay, 1 and 4, 6, 9, 1. 41 times 41. 1 times 1 is 1, 4, 4, 16, 1, 8, 6, 1. Oh no, it broke completely. What happened? Carry! That's exactly right. What happened is you carried. It's because of this little 1 here. And not only because of that little 1 there, that little 1 already affected this, but also these added together. Like the 1 went here and added into that. You see, this 1681 is actually here. This is 1681 like this. I'm going to use some colors. How am I going to do this with colors? I'll try. All right. I'm going to color that one with the 16. I'm going to color this one with the 8. And I'm going to color this one with the 1. And now let me show you where the 16, the 8, and the 1 are. This is the 1. This is the 8. And this is the 16. Do you see what I did? I don't know if you can even see my little 1. My little 1 is a carry. Let me draw it in a way where it's even bigger. Here's the 1, and here's the 8. Does that make sense? So I actually have the 16, the 8, and the 1, because that's exactly what I'd expect. The 16 is what happens when you multiply 4 by 4, and that's what's going on over there. And the 1 is what happens when you multiply the 1 by the 1. That's what's going on there. And in the middle, okay, in the middle is where we get the combination. The combination is the 8. And the 8, by the way, is 2 times 4 times 1. That was this like a plus b whole thing squared has a 2ab in the middle. All right, so the carry breaks it. So the rule of thumb is you can do this swapping thing, and this swapping thing works as long as you don't have any carries to worry about. And really, those only happen to be these few examples that I showed you. So yes, so that's how this whole thing works. This is also how when I was trying to take the square root of 1,000 just now, I was like, I know 30 will be smaller. I know 31, okay, that's going to be 961. And then 32 is a famous number. 32 is a power of 2. 32 squared is a power of 2. It's 2 to the power of 5 squared. That's 2 to the power of 10. And if you do enough stuff with computers, you know that's 1024. And so that's how I knew that the square root of 1,000 is somewhere around 31 to 32. Okay, what could we do next? Let's see. We have a few minutes left. What kind of math problems do we have here? Oh, I did see a non-math problem I'm happy to answer. Somebody asked, why did it take so long to get Novid into the Google Play store? It's a free download, but it's still called a store. The reason is because Google is being very careful, and they should be. They don't want to let random people put COVID-19 apps into the App Store. And so you first need to go and prove that you are legit and that you're actually supported by medical institutions or universities or governments. And so it took us a while to, in fact, even talk to our mayor's office in the city of Pittsburgh. Also, we had to talk to an organization that runs hospitals in Pittsburgh. And we also had to talk to the university. And ultimately, we had to have them all support us and tell Google that this was legit. So that's why that took a long time. Okay. Somebody else asked, Skylar Schreier asked, how does Novid earn money? It doesn't. Actually, Novid's development was entirely funded by the online math classes, which I run. I just started it. I started Novid because I felt it had to be done. I felt that the world was going into a bad place. And because I happened to be in a place where I could say, we can try to use some of this to hire some people to try to solve this problem, we did. So it actually has no current plan of how it will make money. But my goal is, in some sense, if we don't have this problem solved, a lot of us will have major, major issues. So the idea of how to make money was not the first thing that we thought about. Okay, more things. Oh, this is an interesting physical question. What would happen if everyone jumped at the same time at the place they are right now? There's a book about this, but it's not the same scenario. Okay, so you're saying if every single person jumped at the same time, what would happen? Now that's interesting because if you just jump once, I think that would create some kind of a shock wave. In some sense, it would immediately put a shock wave around the Earth. But then that itself is not that big of a deal because the Earth is huge. The thing to know is that the Earth is just huge. It's a three-dimensional object and it's full of stuff, and the stuff is very heavy. So I would expect that if everyone on Earth jumped up and down, not much would happen. On the other hand, if you happen to be on a bridge, please do not do this. So if you happen to go, like if you're in San Francisco, do not go onto the Bay Bridge, have everyone stand on the Bay Bridge, and simultaneously jump up and down. Similarly, don't do this in elevators. I know that some people seem to think it's fun to get in an elevator and have everyone try to jump up and down at the same time. That's not so much fun if the elevator were to break, because something that's maybe worth knowing, I don't know if you ever thought about this, but I didn't think about this for a very long time in my life. But if you're in New York City, and if you're in like a 50 or a 60 or a 70-story tall building, and you're in that elevator, do you realize what's between you and the ground? If you're like 60 stories in the air on one of those super tall elevator shafts? Actually, nothing. So if that elevator had a glass, if it had a glass floor, and you were just like looking down, you would be looking at a huge hole. So yes, it's a very bad idea. So basically the idea of an elevator, it feels safe because the door closes and you can't see what's going on. But it's a long way down. The good thing, by the way, is that people actually figured out ways to physically engineer elevators so that even if the cable broke, the elevator wouldn't go all the way down. This is actually quite creative stuff. So there are lots and lots of safety mechanisms in the elevator. It would actually not really be that easy to break the elevator and have you all plummet to the bottom. However, it's still not a good idea. And don't do this on a bridge. If you do this on a bridge, that shock wave that you send might actually disrupt the bridge and you might all fall into the water. And the reason is because the bridge is not supported in its entire surface. Right? What I said is the Earth is a big three-dimensional solid body. And so if you try to put a pressure on it, that's a solid body. It's all supported. But bridges are actually not fully supported. It's not like the bridge is just on top of land. It's actually, well, it's on top of air, and it's supported by some posts. So that actually it's not designed to take that kind of a shock, which is all coming down at the same time. You know, we are in this week where we're going to be doing some sessions with math counts. So I think I should mention this. This is related to engineering. If you want to be an engineer someday and you want to build bridges, then you start to think about, you know, how strong does a bridge have to be? And I mentioned this because Math Counts is supported by the National Society of Professional Engineers. And so, you know, it makes sense that we're talking about engineering this week. But if you build a bridge, you don't want to build the bridge to be so strong that it could handle, I don't know, like it could handle the Empire State Building suddenly landing on top of it. What's the likelihood that that's going to happen anyway? It's not. I mean, hopefully not. And so what you do with the bridges is you try to build them so that they are strong enough to support what they're supposed to times a certain factor, a safety factor. And so what I mean is, if you now suddenly go and do this kind of a jump, if you have gone beyond the safety factor that they had designed the bridge for, it could be bad. Okay. Oh yes, and that ties back to ratios, because this is what ratios are good for. You see, you build the bridge not just to be strong, as in like it's strong enough to carry 10,000 pounds. Is that enough? No, because a car is like 1,000 pounds or 2,000 pounds. So you could have a bridge and it could have like 10 cars on it, and then it goes over. But then at the same time, you can't just go and say, all right, let's just make the bridge be strong enough to carry X number of pounds, and that's a good bridge. Because suppose you're talking about the Bay Bridge in San Francisco. What does that have? Like 4 or 5 lanes in each direction? And it's really long. So it has to carry tons and tons of cars. So what you use is ratios. You go and say, what would it be like if it was loaded? How many cars is that? And what we will do is we will then take a factor. We'll multiply that load by something, and we'll build the bridge to be able to sustain that multiplied load. And that's a ratio. Okay. Wow, there's a question. What's the probability of you falling on an elevator if you jump on one? So here's what I would say. I'm going to guess that the probability, if you just get in an elevator and you just jump, if you want to know what's the probability that causes that elevator to sink all the way to the bottom and fall, I'm going to guess that probability is around 1 in a billion. And here's why. Because there are 8 billion people in the world. And oh, wait, oh, that's not quite right, because not everyone jumps. Well, no. You know what? If you think about it, I wouldn't be surprised if, on average, everyone in their life has jumped in an elevator before. I mean, you were a kid there are kids, right? And at some point, you might have jumped before. I've probably even jumped before in an elevator. Maybe just not at the same time as everyone else, right? So if I'm saying that there's like 1 billion people who have tried jumping in an elevator, and somehow I haven't heard the news story of person jumped in elevator and elevator collapsed. Since I haven't heard that news story, the chance of it happening is probably about 1 in a billion or less. Because you know, like if actually somebody jumped in an elevator and then the elevator collapsed and the whole thing went down, that would be in the newspaper. The headline would be, somebody jumped in an elevator and the elevator crashed, right? So that's how I'm thinking through this. So my answer is going to be something around like 1 in a billion. So yes, it's unlikely. However, if you ask a different question, what's the chance that you jump in the elevator and then it gets stuck? Now this is much, much higher. I mean, many of us have heard of people who got stuck in elevators before, right? Like you rarely hear about people who had the elevator collapse all the way down the shaft. That's because the engineers designed very good physical systems to make you not have that happen. On the other hand, getting stuck in elevators is a thing that happens. So, oh no, Irfan says I got 2. Andrew Chow says I did. Look at that. We have a live stream with 200 some people. And inside this group, we already have 2 people who have been stuck in elevators before. So what this means is getting stuck is a legitimate, it's a legitimate bad thing. It's a legitimate thing that might happen. If you jump in the elevator, you might get stuck in the elevator. And that's no fun. The reason it's no fun is because it's really hard to get out. So don't do that. Don't get stuck in an elevator. Okay. We have like 2 more minutes. What else can we do? What's some nice question to go and finish up? Oh, yeah. Okay, well, I'll do 2 questions because this one's quick. This one's related. Wang Kevin asks, what happens when an army walks on a bridge? Actually, this is a well-known thing. Whenever an army is marching, an army is supposed to march in formation. Like everyone, this is not aligned. I can't make my fingers walk in formation. I'm not coordinated enough. Now I can. Something like this, right? That's how you're supposed to march. The way you're supposed to march is all the legs are doing the exact same thing at the same time. But whenever an army goes onto a bridge, they are supposed to break their march. They're supposed to not do that march in a perfect order. Or else, they break step on the bridge, says no name. This is correct. So the orders are when you're marching, you march in that exact way. But then once you get to the bridge, you break step. Or else, you break bridge, which is much worse. Okay. Resonance, that's true. It's because the main thing is that this sort of walking on the bridge is going to cause the bridge to start to vibrate. And if you make the bridge start to vibrate at what's called the resonant frequency of the bridge, it starts to vibrate more and more and more. And then there's like one of these movies about, I think it was like it's a video of, I think, the Tacoma Narrows Bridge somewhere in Washington, where when there's like the same type of thing happening, after a while it blows up. It breaks. The same way as a swing. Like swing pushes, thank you very much. So when you push on a swing, if you just like randomly push, nothing much happens. But if you just keep pushing and pushing and pushing at the time that you're supposed to push, soon that goes. And please, when you're using the swing, please do not swing the person over the top of the swing. That's quite dangerous. Snap. Yes. Okay. Well, unfortunately, I guess that looks like we got to the end of our time. But we had some fun today, talking about different aspects of math and how to cross bridges. And hopefully, you now have some idea of how all of these tricks also fit together. We'll be back again tomorrow. Until then, I wish all of you... Oh, okay, I said one more. You want one more? I'll do one more. Okay, I did want to do one more. Let's do one more here. I usually like to end with something that's more soft. Soft meaning it could be just about the general philosophy. So you guys got me back, so I'll give you that one. I did see one that was asked by Muhammad Guelen, asking how to get little kids excited about math. I think that little kids, or actually not just little kids, even adults, get excited about things that look exciting. So I think what our job is, whenever we're teaching math, is to try to show things that are really interesting. You know, like, we did multiplication today. It's just like multiplication problems. Oh, but the ones we chose are interesting. If you choose the right problems to do, then actually there's a beauty in everything. I saw some people in the chat also had commented various times, like, wow, that was beautiful. And the beautiful, it's not my thing of showing you that it's beautiful. It's that the thing is fundamentally beautiful by itself. So if you go and choose the right kinds of questions to do, especially questions that have someone needing to think a little bit, then hopefully little kids can also get excited about math. It's worth it, because once you understand math, you can do lots and lots of things. Okay, well, that finishes our live stream for today for Real Time. We'll be back tomorrow at the usual time, 4 o'clock to 5 o'clock p.m. And then tomorrow is going to be the last normal live stream of this week, so I'm already going to give a heads up. We're going to, on Wednesday, Thursday, Friday, be doing the problems from the chapter competition from this year's Math Counts. If you'd like to get ready for that, please do click on the links on the live stream page, the poshenloh.com/live page, because that happens to have the problem sets that you can work on. I'm actually going to assume that people have already played with the questions, because what we're going to use the time Wednesday, Thursday, and Friday for is we're going to talk about interesting ways to do the questions. Okay? So tomorrow will be the last one this week where we ask like these normal questions or abnormal questions coming from all over. And then Wednesday, Thursday, Friday, we go full steam on this year's chapter Math Counts. See you tomorrow. Have a great day.